Good afternoon, everyone. My name is Haig,
I'm Ryan.
And I'm Nate.
and today we will be explaining a fundamental concept that we learned throughout this week. So, as many of you know, founding father Franklin was very Benjamin Franklin was very well known in his efforts for the American Revolution and his efforts in drafting the Constitution. However, he was not commonly known as a scientist. Benjamin Franklin has done many experiments throughout his career. Um, one that really stands out was one where he was trying to impress party goers. In that experiment, Benjamin Franklin took a cane, and on the bottom of the cane, he put a drop of pure oil slash oleic acid, and took that cane to a lake and put the bottom of the stick in the lake, which then eventually calmed the lake water. And many people throughout history have tried to understand this phenomena, but never really got it. So today we are here to explain the why to this phenomena.
Yeah, so as Haik said, yeah, we're here to explain the why of this phenomenon that people in the past have always seen that oil calms water, oil makes water more stable, but they never really understood why this was. So this is our graphic illustration. And I've always thought that illustrations are really good to like depict scientific things. So here's what we're going for. We're going for, there's two concepts really that's in this illustration. It's the concept of the amphiphilic molecule, which is the cat and the fish, and the concept of indirect measurement, because at the nanoscale, we can't exactly take a super tiny ruler and measure these things because obviously they're tiny. And so the only way we can really measure these things is to measure something that is actually measurable, such as the diameter of something, of like an oil spill, and then we have to extrapolate based on data that we have received. So amphiphilic, we all know amphibian, land and water. We know we're an amphitheater, right? There's two sides. So amphiphilic refers to the point where there's two ends of this molecule. The first end, as we can see with the cat, cats don't like water, so it's hydrophobic end. And we see the tail, which is of a fish, and fish love water, so it's a lipophobic end. And these molecules that we saw of oleic acid they arrange themselves in an order so that they form a one molecule thick layer called a monolayer. And in this case of oleic acid, it's 1.97 nanometers. And what we found was that they naturally stack on, if you put it on water, as Benjamin Franklin did in the lake, it would calm the lake by forming this very small, thin layer on top of the water, calming it. So that's the cat allegory of this part of the representation. The second part that we see is the indirect measurement. We see a man like he's much smaller, and he's holding what we call a surveyor's wheel to measure the length between him and the particle, and he's also holding a protractor to measure the angle. We also did some math, and that's this is one of the limitations where you can't exactly demonstrate the exact form, the exact math that we did, but this is a very good example of indirect measurement, how we can take an angle, take a side, and we can find the height of something by using trigonometry and SOHCAHTOA. So those are really the two aspects that really is covered in this illustration.
So I'm going to go into more in depth about what we actually did in this experiment to find the length of one oleic acid molecule. So what we calculated first is we found the volume of the oil we're going to drop on the water, and then we measured the diameter of the oil when it spread across the tub of water. And because it's a monolayer, we know it's like a cylinder where the radius is the oil spill, but the thickness is only one molecule thick. So if you know the volume that you dropped into the water, and you know the radius of the circle, you can find the height. which ended up being 1.97 nanometers. And the interesting thing about this number is how small it is in comparison to everything else. So it would be impossible to view this with the naked eye or even with a light microscope, as the smallest wavelength of light is about 400 times larger than the molecule itself, so it would be actually impossible. But you can do it with advanced electron microscopes, but not many people have these. So it's really interesting how you can calculate something so small using standard math and critical thinking. To give you some scale about how small this actually is, 1.997 nanometers is to a soccer ball as a soccer ball is to the entire planet Earth. So this number is so insignificantly small. However, we're able to determine it using nothing but our heads, which is really interesting. And this is the fundamental principle of nanoscience, where a lot of the times we can't actually measure what we're looking at. Thank you.
So yeah, questions?
So I was wondering, why is it that one end of the particle is attracted to the water, but the other end isn't?
Right.
All right. So if we delve into the physics, or not really, the chemistry of how the molecules, one end is polar and one end is nonpolar. And if you see in the substance that is, it's water, right? Water is polar, and polar things like other polar things, while nonpolar things like nonpolar things. It's kind of like a magnet. So if you arrange these items jumbled together and just put them into this medium where it is separated, the nonpolar side would like the nonpolar side, and the polar side would like the polar side. Therefore, what we see is that the molecule will orientate itself so that the polar side would be in the water, and it will be one cell thick.
Okay, but let me just add to that. Can you define polar?
Yes. So polar, it's a chemistry topic where electrons aren't distributed evenly across a molecule. So certain atoms, like oxygen, are very grabby. They like to pull the electrons very close to themselves. This makes the atom slightly negative because electrons are negatively charged. And that means the other side of the molecule is positive. So it's a very slight differentiation in charge. And this is why water forms hydrogen bonds. And it's actually really important for how water works and how chemistry works in the real life. So on an oleic acid molecule, it has an oxygen and hydrogen group at the end, which makes it polar. And the rest of it's just carbon and hydrogen, which does not share electrons unevenly, which makes it have no charge and thus nonpolar.
That was an awesome description. You could come teach freshman chemistry here. Okay, other questions?
How much margin of error do you think you have in your measurements? Because dealing things on this scale, even if you're off by a little bit in your volume or in the radius, it could mean the thickness of the molecule could be off by quite a bit.
Yeah. So what we found in our experiment was that sometimes we would get the value of 1.97, but we wouldn't get that value. We would get that value multiplied by maybe 4, so we get 8, or maybe by 5 we get 10. So then we could see that, oh, we didn't mix the oil and the water because we diluted the oil well enough so that when we put it onto this medium, which is water, it actually formed not a monolayer, but a layer of 5 molecules instead of what we intended for, which is 1. And again, also, if you don't mix properly, you won't get a circle, but rather you'll get an irregular shape. So that will also maybe screw up your calculations.
There's a very fine, it's a very fine measurement, and we got quite a bit of error, but we did multiple trials, but we got relatively close. We were within I think 10 nanometers, which it is very small, but considering we were measuring using rulers and graduated cylinders that weren't even perfectly accurate, it was really surprising how close we got.
But I actually think you guys said the right answer, which is way bigger error than whether you exactly measured it right, was whether you have a monolayer or a bilayer or a trilayer, because there are other ways to arrange. But order of magnitude is actually good at this length scale. So within the right factor of 10, you're doing awesome. Okay, is there one more question? Well, I have a question. If you. Okay, so well, I will ask my always question, which is, so what are the limits? So I have actually two questions. My first question, which you can answer as my real question, is, so what are the limitations of this experiment? It describes many aspects of what you did, but not all aspects of it. And then my second question is, why does a monolayer of oleic acid on a surface of lake calm the waters of the lake? Not that you necessarily need to know lake hydrodynamics, but I would like to know what Benjamin Franklin was actually doing.
All right, so I can tackle the first one. So
Yeah.
there's
The,
a couple-
the second one you don't actually have to answer because
All right.
I don't think we know the answer to that.
So there's a couple limitations that I think that I see, especially because this is not the way that we actually calculate the thickness of this molecule. We did not calculate it in a triangle and use trigonometry. We actually used, as Ryan said, we calculated it as a cylinder, as just a really thin cylinder. And the other thing is that we only see one molecule rather than multiple molecules arranged together in one monolayer. So yeah, I think those are two limitations that I see.
That's good. Any guesses on why a monolayer of molecules would calm a lake?
Is it because like the hydrocarbon tails, they're attracted to each other, and it's stronger than like all the water that's shifting around, and it smooths it out?
I don't know the answer. I mean, the hydrocarbon tails do interact, and there is some cohesive interaction, but it should be an energy that is so astronomically low compared to the energy of a wave that I can't quite see why it would do any good. But I'm going to take olive oil next time I go to a lake and see what I can do. Okay, thank you guys.
Thank you.